Hello, and welcome to our Multimedia Applications and Virtual Reality course. This section focuses on the haptic dimension of VR, which enables touch-based interaction and force feedback to enhance realism and user presence. Perception in the physical world is direct and natural, arising from unmediated sensory contact with our environment. In contrast, perception in a virtual world is interfaced and illusory, constructed through technological systems that substitute real stimuli with artificial ones. This mediated perception enables the user to explore virtual environments in two ways: passively, through observation without influence on the environment, or dynamically, through interaction that allows the user to act upon and modify virtual entities. Interaction in virtual reality is therefore driven by user decisions, which are made on the basis of perceived stimuli originating from multiple sensory modalities, such as vision, audition, and haptics. These multimodal data inform the user's interpretation of the virtual world and guide their actions within it. The haptic dimension represents the final and most embodied stage of this interaction process, as it closes the perceptual action loop by allowing the user not only to perceive the virtual environment, but also to physically engage with it through touch and force feedback. Why do we use haptics in virtual reality? Haptics in virtual reality, or VR, serve two primary purposes: locating the user's body within the virtual space and enabling meaningful interaction with virtual objects. For spatial localization, the system must determine both the position of the user's body, typically captured through motion tracking technologies, and the posture or configuration of the limbs, which may be inferred through segmentation techniques and advanced image analysis algorithms. To act upon virtual objects, VR systems rely on effort-based input mechanisms and haptic feedback devices. These technologies allow users not only to manipulate elements within the virtual environment, but also to receive tactile or force-related responses that simulate real-world physical interactions. This reciprocal loop of action and feedback significantly enhances realism, precision, and immersion. In virtual reality, the haptic dimension refers to all interactions related to the human sense of touch, understood in its broadest meaning. Unlike vision or audition, haptics involves multiple sensory subsystems that together allow users to feel, move, and physically engage with virtual environments. First, proprioception enables users to perceive the position, posture, and movement of their body and limbs in space. In VR, this sense is continuously stimulated through motion tracking and spatial consistency, allowing users to feel that their virtual body corresponds to their real one. Closely related is the vestibular sense, which governs balance, head orientation, and sensations of acceleration or deceleration. Although VR systems cannot directly stimulate the inner ear, they can induce vestibular illusions through visual motion, synchronized movement, or motion platforms, contributing to immersion, or, if misaligned, to discomfort. The tactile sense concerns surface contact and pressure perceived through the skin. In VR, tactile feedback is typically produced using vibration, pressure, or texture simulation to convey contact with virtual objects, buttons, or surfaces. Kinesthesia refers to the perception of movement and effort originating from muscles, tendons, and joints. Haptic devices, such as exoskeletons or articulated controllers, stimulate this sense by resisting or guiding motion, enabling users to feel weight, inertia, or constraints. The broader cutaneous sense encompasses all sensations arising from the skin, including pressure, temperature, and pain. While pressure is commonly simulated in VR, temperature and pain are generally limited or avoided for safety reasons, yet they remain important research directions. Finally, force feedback represents the technological means by which many of these sensations are delivered. Through motors, actuators, or brakes, force feedback devices apply controlled mechanical forces to the user, providing kinesthetic and tactile cues that are tightly synchronized with visual feedback. Together, these haptic concepts form a multi-layered sensory framework that transforms VR interaction from simple observation into embodied experience, reinforcing realism, presence, and meaningful interaction. Human tactile perception is based on 4 fundamental modalities of cutaneous stimulation, each associated with specific types of skin receptors. Together, these modalities constitute the physiological foundation of all tactile sensations and guide the design of haptic interfaces. Mechanical stimulation arises from the physical deformation of the skin, such as pressure, touch, vibration, stretching, shear forces, and texture. These sensations are detected by mechanoreceptors, including Merkel cells, Meissner corpuscles, Pacinian corpuscles, and Ruffini endings. Most contemporary haptic devices rely primarily on this modality, as vibration, pressure, and surface deformation can be reproduced reliably and safely using electromechanical actuators. Thermal stimulation corresponds to the perception of heat and cold and is mediated by thermoreceptors sensitive to temperature variations. Although less common than mechanical feedback, some haptic systems incorporate thermal cues using electrothermic elements, conductive heating or cooling surfaces, or phase change materials to enhance realism in virtual environments. Chemical stimulation involves the detection of irritants, pH changes, or specific molecules at the skin level, and is closely linked to sensations such as pain and itch, as well as protective reflexes. Due to its slow, unpredictable, and potentially unsafe nature, chemical stimulation is not used in haptic devices for virtual or augmented reality and remains confined to medical or experimental contexts. Electrical stimulation, also known as electrotactile stimulation, uses controlled electrical currents to activate cutaneous nerves directly, producing sensations such as tingling, tapping, or artificial touch, and in some cases inducing proprioceptive illusions. This modality is increasingly explored in modern haptic systems because it enables lightweight, silent, and fast feedback without the need for mechanical actuators. Haptic devices can be categorized according to how they generate and apply reaction forces to the user, with 2 primary implementation strategies: non-grounded or internal reaction systems, and grounded or external reaction systems. Each approach presents distinct advantages, limitations, and practical applications, particularly in virtual reality environments. Non-grounded or internal reaction haptic devices produce forces and tactile effects using the user's own body as the reaction base. These devices are worn, held, or attached directly to the user without requiring any physical anchor in the environment. They include wearable items such as gloves, sleeves, vests, belts, or handheld controllers. Non-grounded systems provide a high degree of freedom of movement, making them well-suited for room-scale or mobile VR experiences. Depending on the actuator type, which may involve motors, pneumatic systems, or shape memory alloys, these devices can be bulky, heavy, or energy-intensive. While they are particularly effective for delivering tactile feedback, they can also produce limited kinesthetic forces through internal resistance mechanisms. Grounded or external reaction haptic devices operate by applying forces against a fixed structure, such as a desk, platform, or robotic arm. This anchoring allows these systems to generate stronger and more precise kinesthetic feedback compared to non-grounded devices. Grounded systems are physically constrained within a defined mechanical workspace, which limits the user's freedom of movement, but the off-body placement of actuators often results in a lighter and easier to manipulate interface. They are particularly suited for applications that require precise force control, such as surgical training, virtual prototyping, teleoperation, and scientific simulation. Together, these two classes of haptic devices illustrate the trade-offs between mobility and force precision in virtual reality applications. Non-grounded systems prioritize user freedom and tactile immersion, while grounded systems focus on delivering accurate and robust kinesthetic feedback. Understanding these distinctions is essential for selecting the appropriate technology for a given VR application or experimental scenario. In virtual reality systems, it is important to distinguish between effort-based input mechanisms and haptic feedback devices, as they play complementary but opposite roles within the interaction loop. Together, they form the sensory-motor link between the user and the virtual environment. Together, effort-based input mechanisms and haptic feedback devices form a bidirectional interaction system. The first captures the user's physical intention, while the second conveys the system's response back to the user, enabling natural, intuitive, and immersive interaction in virtual reality environments. Effort-based input mechanisms correspond to the direction of interaction from the user toward the system. These mechanisms define how the user acts on the virtual environment by expressing an intention through physical effort. When we say that effort-based input mechanisms describe how the user acts, we refer to any voluntary physical action performed to influence the virtual world. This action may involve pressing, pulling, moving, or activating muscles. The system does not yet generate sensations at this stage. Instead, it observes and captures what the user is doing. The primary purpose of these mechanisms is therefore to detect user actions as accurately and reliably as possible. From a technical perspective, effort-based input mechanisms are characterized by their ability to measure user-generated signals. These signals can take different forms, such as forces applied to an object, movements of the hands or body, or muscle activity produced during an action. By measuring these physical quantities, the system obtains raw data that represent the user's effort. These mechanisms serve as input channels that allow the user to control or manipulate virtual objects. For example, the intensity of a force may determine how strongly an object is pushed, or the direction of a movement may define the trajectory of a virtual tool. In this sense, effort-based input mechanisms act as translators between the user's physical actions and the virtual environment's control parameters. Beyond simple measurement, these systems also interpret user intention. The collected signals are processed to infer what the user wants to do, such as grabbing an object, applying pressure, or initiating movement. This interpretation step is essential to enable intuitive and natural interaction within VR. Several examples illustrate this concept. A VR controller may sense the pressure applied to its trigger, allowing the system to distinguish between a light action and a strong one. A force sensor can measure how hard the user pushes or pulls on a virtual object, directly mapping physical effort to virtual response. Data gloves can detect finger flexion forces, enabling realistic hand-based manipulation. Finally, EMG-based interfaces go one step further by reading muscle activation signals, allowing the system to infer effort even before visible movement occurs. In summary, effort-based input mechanisms capture the physical expression of intention from the user and transform it into meaningful input for the virtual environment. They represent the first and essential step in the interactive loop of virtual reality. Haptic feedback devices correspond to the direction of interaction from the system toward the user. These devices define how the virtual environment responds physically to the user's actions. When we refer to haptic feedback devices as describing how the virtual environment responds, we mean that the system actively generates sensations perceived by the user's body. Unlike input mechanisms, which only observe the user, haptic feedback devices intervene by stimulating the user's sensory system in order to convey information about virtual events or object properties. The primary purpose of haptic feedback devices is to provide tactile or force sensations back to the user. These sensations act as substitutes for real-world physical interactions that would normally be felt through direct contact with physical objects. By reintroducing touch and force cues, haptic feedback devices close the interaction loop and reinforce the sense of presence within the virtual environment. From a technical standpoint, these devices are characterized by their ability to generate different types of sensory cues. Tactile cues include vibration, surface texture, or temperature changes, which stimulate the skin and convey information about contact or material properties. Kinesthetic cues involve resistance, force, weight, or torque, and stimulate muscles and joints, allowing the user to perceive object mass, stiffness, or constraints. Together, these cues enhance realism by mimicking or substituting real-world physical responses that would normally arise during interaction. Several practical examples illustrate these principles. A controller may vibrate when the user hits or touches a virtual object, signaling contact or impact. A force feedback joystick can resist the user's movement, simulating obstacles or mechanical constraints. A haptic glove may reproduce surface texture or pressure, enabling the user to feel virtual objects during manipulation. In more advanced systems, a VR exoskeleton arm can apply torque to the user's limbs, creating the illusion of weight or resistance. In summary, haptic feedback devices transform virtual events into physically perceivable sensations. By conveying touch and force information from the system to the user, they play a critical role in enhancing realism, immersion, and embodied interaction in virtual reality environments. Tactile displays, also referred to as cutaneous haptic systems, aim to simulate the sensitivity of human skin by generating surface-level sensations. Unlike force feedback devices that act on muscles and joints, tactile displays primarily stimulate skin receptors to convey information about contact with virtual objects. One of the most fundamental tactile cues is pressure, which allows users to perceive contact, surface texture, and object compliance. By applying localized pressure to the skin, these systems can create the illusion of touching solid, soft, or deformable virtual surfaces. Vibration is commonly used to represent roughness, impacts, or surface irregularities. High-frequency vibrations can simulate fine textures, while short impulses often indicate collisions or discrete events in the virtual environment. Thermal stimulation introduces sensations of heat and cold, providing material-related cues such as metal, ice, or warm surfaces. Even small temperature variations can significantly enhance realism by reinforcing visual information. Tactile displays can also reproduce physical touch, such as objects pressing against the skin or moving across it. This category includes dynamic contact patterns that support sliding, tapping, or brushing sensations. More advanced techniques include skin stretch and shear, which generate directional cues related to friction, motion, or slip. These cues are particularly effective for conveying movement across surfaces or object manipulation. Emerging technologies expand tactile feedback beyond direct contact. Ultrasonic mid-air haptics use focused ultrasound to create contactless tactile sensations in free space, while electrotactile stimulation applies controlled electrical impulses to simulate pressure or complex textures without mechanical actuators. Additional approaches include pneumatic or air jet feedback, where pulsed air simulates touch or airflow, and soft robotic actuators which deform to convey squishiness and elasticity. Finally, vibroacoustic or resonance-based haptics rely on high-frequency vibrations to reproduce fine textures and sharp impacts, further enriching tactile interaction in virtual reality. Force feedback devices, also known as kinesthetic haptic displays, apply controlled mechanical forces to the user's body in order to simulate physical interaction with virtual objects. Unlike tactile displays that stimulate the skin surface, these systems act on muscles and joints, allowing users to feel forces, resistance, and motion constraints. One of their primary roles is to resist user movements, thereby simulating physical properties such as weight, inertia, stiffness, or mass. By opposing motion, force feedback devices create the sensation that a virtual object has substance and mechanical behavior. These systems can also constrain motion to reproduce collisions or the presence of solid surfaces. When a user reaches a virtual boundary or obstacle, the device limits movement accordingly, reinforcing the illusion of contact with a rigid object. Force feedback devices may additionally apply directional forces that guide motion or indicate virtual object properties. Such guidance is particularly useful in training or rehabilitation scenarios, where forces can assist, correct, or resist user movements in a controlled manner. Advanced force feedback technologies allow the simulation of deformable or soft objects. Soft robotic actuators, made from flexible materials such as silicone or electroactive polymers, deform under interaction to convey elasticity, compliance, or squishiness, closely resembling real-world soft materials. Other approaches rely on shape memory alloys, which change shape when electrically activated. These materials enable localized or finger-level resistance and are well suited for wearable devices, such as haptic gloves or soft exoskeletons. Exoskeleton-based systems extend force feedback to the fingers, hands, or arms, providing precise resistance and movement guidance. Pneumatic or hydraulic systems use fluid pressure to apply larger forces and are often employed in full-body configurations. Electromechanical linear actuators, on the other hand, offer high-precision force or torque and are commonly found in desktop or training simulators. Finally, force feedback can be integrated into larger platforms, such as haptic chairs or locomotion systems, to simulate body motion, impacts, or environmental effects. Hybrid devices further enhance realism by combining kinesthetic force feedback with tactile stimulation, creating a more complete and convincing sensory-motor experience in virtual reality. Many haptic and force feedback devices remain inherently cumbersome due to their mechanical complexity, size, and weight. These systems often require rigid structures, multiple actuators, and external support frames, which can limit portability and user comfort. As a result, their integration into everyday virtual or augmented reality applications must carefully balance performance with ergonomics and practical deployment constraints. The installation of haptic systems raises important technical and safety considerations, particularly regarding electrical conductors, power delivery, and actuator behavior. Improper insulation, cable management, or control errors may expose users to electrical hazards or unintended mechanical forces. Consequently, strict safety standards, fail-safe mechanisms, and real-time monitoring are essential to ensure reliable and secure operation during human interaction. The degree of motion freedom offered by a haptic device significantly influences both realism and usability.
Grounded systems, fixed to an external structure, can generate high forces and precise constraints, but restrict user mobility. In contrast, ungrounded or wearable devices offer greater freedom of movement at the cost of reduced force output and stability, requiring careful design trade-offs depending on the application. The magnitude of haptic stimuli determines the intensity and realism of the perceived interaction. Insufficient force or feedback may fail to convey meaningful physical properties, while excessive stimuli can overwhelm the user or distort perception. Designing effective haptic systems therefore requires precise control over force, pressure, and vibration amplitudes to achieve perceptual relevance without compromising comfort. Crucially, all haptic stimuli must be modulated within the physiological and perceptual limits of the human body. Muscles, joints, and sensory receptors have well-defined tolerance thresholds, beyond which discomfort, fatigue, or injury may occur. Respecting these limits through adaptive control strategies and user-specific calibration ensures both safety and long-term usability while maintaining a convincing and immersive sensory motor experience.